In this video, I'm going to introduce one of the models that we use to explain kinetics, and that is collision theory. One of the main ideas of collision theory is that the rate of a reaction is proportional to the rate of reactant collisions. So we can write our mathematical expression like this, where we see that our reaction rate will increase as the number of collisions over time increases. And this helps us explain why changing the concentration of reactants changes the rate. And so if we think about the rate of a reaction being affected by the collisions that occur that are productive, the lower the concentration, the fewer collisions you will have, and the lower the rate. The higher the concentration, the more collisions you will have, and the faster the rate. Another aspect of this model is understanding the orientation of collisions. So what we mean by that is that the reacting species have to collide in the correct orientation that allows contact between the atoms that will become bonded together in the product. So in this example, we're seeing a collision between carbon monoxide and molecular oxygen. The bond that's going to form is between the carbon atom on the carbon monoxide and one of the oxygen atoms on the molecular oxygen. If the molecules collide in this orientation, there's no bond that's going to form between these two atoms. So the reaction, in order for the reaction to happen, we need the collision needs to be between the correct atoms. So the orientation of the two reactant molecules matters in order for the reaction to proceed. Finally, we have to consider the energy of collisions. Collisions have to occur with enough energy to allow mutual penetration of the reactant's valence shells. So in other words, you have this atom here and you have valence electrons. And you have this atom here and you have valence electrons. When they collide, there needs to be enough overlap between the two so that they can share electrons. And that is where the chemical bond forms. So the energy of the collision has to be high enough in order for this to happen. Now, this is explained really well with kinetic molecular theory. So in other words, the higher the kinetic energy, the more likely the collision will have enough energy in order for it to be productive and the new chemical bond to form. So here's another way of looking at the kinetic energy or speed of the molecules in our reaction vessel. So here we have a fraction of molecules and we have the kinetic energy or speed. And at any given temperature, we will have a curve like this. So remember that in a given sample, not every molecule has the same kinetic energy. There's a distribution of energy states. And let's say that in order for the reaction to occur, that's the energy required. So we would call that the activation energy or the energy of activation. In order for a reaction to occur, the molecule needs to have this much kinetic energy. So the lower the activation energy, the easier it is for the fraction of molecules to achieve the kinetic energy for the reaction to take place. Or, in other words, the lower the activation energy, the more molecules are at the that meet that threshold, right? So you can see that if we have a lower activation energy, there's more molecules. Another thing you can do is just raise the temperature. So if you raise the temperature, T2, and you look at the area under this curve, it's much higher for the black line. So more molecules have the right kinetic energy, like the minimum level of energy required for the reaction to take place if we raise the temperature. So what this model is really explaining is we're taking this idea of our molecules as particles that collide with each other. And we have experimental data that tells us that as we raise the temperature, the rate of the reaction increases. We can see this in a lab. And so what we do is explain that phenomenon with a model. And that model is these molecules act as particles and they must collide with enough energy in order for the reaction to take place. So let's add one more piece to this puzzle, and that is collision theory and the transition state. So when a reactant species collides with both the proper orientation and adequate energy, they combine to form this unstable species, and you may have heard of it as the transition state or the activated complex. So these are very short-lived, very unstable, usually undetectable by most analytical instruments. That is the transition state or the activated complex. And in some cases, we can observe these, but rarely. So again, this is part of our model. So you can look at this, and there are two examples. This is one reaction, this is the forward, and this is the reverse reaction. So in an exothermic reaction, the energy of your reactants is higher than the energy of the products, and energy is released. And in an endothermic reaction, the energy of the products is higher than the energy of the reactants, so energy is absorbed. Note, however, that in both cases, the transition state or activated complex has greater energy than the products. That is true for both endothermic reactions and exothermic reactions. So let's take a closer look at this reaction diagram. So we start with a system of reactants only, and on our diagram here, we're at A plus B. So these are our two reactant molecules. On the y-axis, we have energy. So as we go up the y-axis, energy is increasing, and this is the extent of reactions. You could kind of think of this as time on the x-axis. So for how long is this reaction going? Or if you want to think about only one set of molecules, then it would be preceding the time for that one specific reaction. And our transition state is that high energy unstable complex. And once the molecules reach the transition state, then it's a downhill to get to the product. So this is true whether it is an exothermic or endothermic reaction, because the difference between the transition state and the product is always going to be negative. The Arrhenius equation can be used to relate the activation energy and the rate constant. So we'll talk more about rate constants as we move through the kinetics chapter. But for now, you want to know that it is a given constant that does not change except for temperature. So if you have a given reaction at a specific temperature, that K will be constant. A is called the frequency factor or Arrhenius factor. It is some constant ratio. It's not a ratio. It's a constant proportionality constant is what it is. This is the number E. And this E sub A is our energy of activation. So this right here is equal to this, the difference in energy from the transition state and our reactants. R is the gas constant in joules per mole Kelvin, and T is the temperature in Kelvin. So this is a really interesting equation because it allows us to experimentally investigate some of these reactions. So if you collect data and you graph the inverse of temperature on the x-axis and the natural log of K on the y-axis, then the slope will be your negative E sub A over R. So E sub A is always a positive value because you go from your reactants up to the transition state. So E sub A is always positive, and the slope of this line is negative. So it is a negative E sub A over R. So what you will do is if you multiply your slope by negative R, you will get the activation energy for your reaction. So I want to talk for a second about catalysts and specifically enzyme catalysts, although this is really true for any catalyst. And that is that what they do is they actually change the activation energy of a catalyzed reaction. And this is the model that we use to explain how enzymes work. So in this scenario, our reactants have a higher energy than our products. So the delta G for this is negative, right? Our reactants and our products are here. And so this is delta G, but you could graph this as delta H. I don't know what the actual delta H is for this example reaction, but you could use delta H instead of delta G. And we see that this is a thermodynamically favorable reaction, right? So the energy of our reactants is greater than the reactants of our products. And so remember that for reactions to occur, the delta G has to be negative. Now the enthalpy could be positive, but that would mean that the entropy would have to make that up and give us a negative delta G. Okay, so in this scenario, we are looking at just the delta G, and we are seeing that our reactants are at a higher energy than our products. Okay, so this reaction can take place. Good to know. So here is the activation energy of the uncatalyzed reaction, which means that in order for reactants to form that transition state and then go down the hill to form product, they have to get this much energy. So the energy of activation is much higher, so you might need to have a higher temperature or some other way of increasing the collisions, like increasing the concentration. But that isn't really going to work inside the body, for example, or if you're working with small amounts of compound, like an expensive thing that you want, expensive drugs that you want to make. What if the kinetics, the concentrations don't lend themselves to anything that happens on a reasonable time frame? Well, that's what the catalyst does, is it actually lowers this activation energy. And so notice that the delta G of the reactants and the products is the same. Okay, so we haven't affected thermodynamics at all. We have only changed the kinetics. So a catalyst only can change the rate of the reaction, and it does that by primarily by lowering this activation energy. So now more particles will meet that threshold and be able to form that transition state and then form product. So to recap, collision theory states that in a reaction vessel, our molecules are represented by particles that collide, and they must collide with enough energy and in the correct orientation to form that transition state, which then decomposes to form products. And that the ways to increase collisions, we could use a catalyst, we could increase the temperature, we could increase the number of particles, or basically increase kinetic energy, right? So that's what increasing the temperature does. So more collisions usually leads to more effective collisions, which leads to a faster rate.